All right, hi everyone. This is lesson 26, example problem number 1. We're given a beam with a pin support at A roller support at B, two forces, a 12,000 and a 7,000 pound force pushing down. Then the problem asks us to solve for both the reaction forces, which you should be familiar with how to do, and then drawing the shear and moment diagrams. So really this problem is about the shear and moment diagrams, so I'm going to go through the solution for the reaction forces pretty quickly, right? So A is a pin support, so we have both a X and Y component for that. B is a roller support, so we just have a Y component. We look at some of the forces in the X direction is equal to 0 because this is statics. The only force in the X direction is the X component of A. Therefore, the X component of A is equal to 0. Next, we have some of the forces in the Y direction is equal to 0. That's equal to AY minus 12,000 pounds minus 7,000 pounds minus BY is equal to 0. One equation, two unknowns, so we need to do our moment equation. So we're going to do sum of the moments is equal to, sum of D times F is equal to 0. We're going to sum moments around point A. So that's going to be equal to negative 12,000 pounds. Sorry, I'm defining counterclockwise rotation as positive. So negative 12,000 times 5 feet minus 7,000 pounds times 11 feet minus BY times 20 feet. So we go through that, we get that BY is equal to 6,850 pounds. We plug that in back above, we get that AY is equal to 12,150 pounds. All right, so far so good. We've got our reaction forces. So next up is drawing the shear and moment diagrams. So the way I like to do this is I'm going to redraw our beam just as a flat line, and I'm going to add all my forces. So I have my upwards, 12,150 pounds. Then 5 feet away, I have my downwards, 12,000 pounds. Then again, I have my that one is a downward. Get rid of all of that. Downward, 7,000 pounds. And finally, an upward, 6,850 pounds. So for the graphical method of determining shear, or for graphical method of drawing our shear diagram, we're going to draw our y-axis, which is our shear, and our x-axis, which is our distances. And again, this was 5 feet right here, this was 6 feet right here, and this was 9 feet right there. So again, in converting those into coordinates, if this is at 0, then this is at 5 feet, 11 feet, and 20 feet. So we have our x, and we have our shear, and shear is usually given as a V. So the way we're going to do shear is we're going to start from the left, move to the right, and we're essentially just integrating our force, right? So every time we hit a force, we're going to adjust our shear. So we start at 0, and you start at 0. So our first force is a positive 12,150 pounds. So we're going to go up 12,000, it's bad writing, 12,150 pounds. And then we have no forces for a while, so we're just going to keep going. Next, we hit a negative 12,000 pounds. So we're going to drop down by 12,000 pounds. And if we were at 12,150, that means we're now at 150 pounds. And then we have no forces for a while, and then we hit a negative 7,000 pounds. So we're going to drop down by 7,000 pounds. So 150 minus 7,000 is negative 6,850 pounds. And then we're going to keep going for a while, And then at the end of our beam, we hit our positive 6,850 pounds, which is going to bring us right back up to 0. And then we have our shear diagram. So a couple things to notice about this. One, it starts at 0 and it ends at 0, right? That has to happen every time. If it doesn't, it means you've done something wrong. Other things to point out, yeah, that's pretty much it for the shear diagram. They're not too bad. Again, you just move left to right, go up or down every time you hit a force. So next up, we want our moment diagram. So mathematically, the moment diagram is equal to the integral of the shear diagram. So if you remember back from calculus, the integral is really just the area under the curve. So we could come up with an equation for shear as a function of x and do an integral, but that's more complicated than we want this to be for dirt, right? So if it's area under the curve and we look at our shear diagram, it's just a bunch of rectangles, right? So our first rectangle is 5 feet across. Didn't mean for that to shift. And 12,150 pounds high. Therefore, the area of that section, right, is 60,750 foot-pounds. If we go ahead and look at our next section, it's 6 feet across, it's 150 pounds tall. Therefore, the area under that section is 900 foot-pounds. So then we look at our last section and we see that it's dropped into the negative, right? So it's 9 feet across and it's negative 6,850 pounds tall. Therefore, negative 6,850 times 9 is negative 61,650 foot-pounds. All right, so knowing this, we can go ahead and we can draw our moment diagram. So goes across, we have X and we have M. Now we know those important points, right, are going to be at 5 feet, 11 feet, and then our last one is at 20 feet. All right, so mathematically, if you remember back to calculus, the integral of a constant is just that constant times x. So that's a linear function, right? If we go look at our first section between 0 feet and 5 feet, the shear is constant going all the way across. So when we integrate a constant, we get a linear shape. So it should be a nice linear slope. And we know that by the time we get to 5 feet, the moment has added up to 60,750. I'm just going to say the whole thing's in foot-pounds. I don't want to try to keep squeezing foot-pounds into my axes. Okay, so then we go to a lower constant, so that's going to translate into a smaller slope as it continues to go up and up and up. And then if we go to mark that on our y-axis as well, that would be 6,750 plus another 900 gives us 61,650 foot-pounds. Then our shear drops into the negative, so our moment needs to start going down because we're subtracting away. And if you'll notice, it was negative 61,650 foot-pounds. We're starting at 61,650 foot-pounds. So we go all the way back down to 0. All right, so interesting things. One, just like shear, moment has to start and end at 0. What that means is when you look at your shear graph, the area under the shear graph in the positive half, right, over here, has to be numerically equal to the area under the curve on the negative portion on the right side. That way, when you do the integral going all the way across, you end up with your moment going up and up and up and then right back down to 0. So we're going to do a couple more examples like this. Shear is not always just straight horizontal lines. So sometimes you can end up with behavior for moment that's not just linear ups and linear downs. But this is your kind of base starter example. All right, thanks.